Hello and welcome back to Math 152. We're going to continue our study with Chapter 3 today. Let's get started. We're going to talk about measures of spread, Section 3.2. In Section 3.2, we're going to talk about several things. We're going to talk about what the range of a data set is and how to compute it. We're going to compute the variance of a population in a sample. We have to learn what a variance is, the standard deviation of a population in a sample. We're going to do those two different ways. Approximate the standard deviation with group data, just like we did the mean using group data in Section 3.1. We're going to approximate what a standard deviation was with that group data. Use the empirical rule to summarize data that are unimodal and approximately symmetric. We would like to be able to say things about where the data lies in general. And then we're going to use this Chebyshev's inequality to describe a data set that's really not symmetric. So the first one, empirical rule to summarize data that are unimodal and approximately symmetric. If it's not symmetric, we're going to shift over to Chebyshev's inequality to help us. And then finally, we're going to compute the coefficient of variation, and that's going to give us some relative spread of the data. But if we have two different sets of data, how do those two different ones this will give us some idea of how they spread compared to each other. So what is the spread? So let's talk about compute the range of a data set. So the range of a data set, and in this, let me make a kind of a general statement before we get started. I'll pull the stat right down here. With spread, I am talking about how spread out the data is. If I could have two data sets that have the very same mean and the median if it's symmetric, one could be all the very same value, all the data sets were the same value. The other one is really spread out all over the place, very wide, but the average is the same. And we would like to know ways that we can describe how spread out this data is and in relationship to one another, and just to be able to have some values. In general, the data set, if I know the measure of center, the mean, and if I know the standard deviation, I can tell how tightly it's clumped around that mean, how the data feels, and that's kind of what this is all about, is describing how spread out. So our first one is the range of a data set, and that's just basically the difference between the largest value and the smallest value. So here the average monthly temperatures in degrees Fahrenheit for San Francisco are listed. Here's the different months we go through, and here's the average temperature for that month, and it goes all the way through. So the range is basically the largest value, the difference, the subtraction between the largest value and the smallest value. So given my data set, I want to go through the data and look for the largest value. Then we'll go back through, find the smallest value, and then I'm basically going to subtract the smaller from that larger. So 63 minus 51 is 12. That gives me the range of the data. So that tell me where, it's not like if you were thinking the range of today's temperatures is 51 to 63 degrees. It is more of the max minus the min. What's the difference between the maximum and the minimum in there? So if the range of temperatures had been 63 and 0, you'd have had a spread of 63. That was the range. So that's how you measure it to calculate the range. Okay. So although the range is easy to compute, is not often used in practice. The reason is that the range involves only two values from the data set, the largest and the smallest. And what we want something is more of where most of the data is spread out, how most of the data is spread out, not necessarily those outliers that one lottery win. Okay? So what's going to help us with that is, first step we're going to go through, we're going to talk about the variance, and then we're going to find that the standard deviation is more often used. It's able to compare directly with the mean, the same units, and but we have to go through this process for the variance to get the next objective, the standard deviation. Go back down here again. So variance. When a data set has a small amount of spread, like the San Francisco temperatures, most of the values will be close to the mean. When a data set has a larger amount of spread, more of the data values will be farther from the mean. The variance is a measure of how far the values in a data set are from the mean on the average. It's kind of like the average distance of from the mean. And then I can kind of do some calculations based on that. So the variance is computed slightly differently for populations and sample, and the population is going to be done first. You're going to have to be really careful with this to understand, are you talking about population data, sample data? It is very close, except there's going to be one little parameter that we're going to have to tweak in there. So our population variance, here's our data set numbers again. You remember I used those subscripts before to denote the different numbers, x sub 1, x sub 2, all the way out to x sub n. Denotes the values in a population of size n. There's that big capital N just to say here's the numbers. So here I have to be very careful. I'm talking about the population. I'm going to calculate it in this way. If this was sample data, I'm going to tweak some numbers down here, so we'll have to pay attention. The population variance, this is the little sigma squared, okay? And this is the variance. When I see that squared, that's the variance portion of it, okay? And what we're going to do is I'm going to go and find the population mean first. And for each one of these data points, and then after I get the mean of everything, I'm going to go back, subtract that data point from the mean. How far is it from the mean? And I'm going to do this for each data point. I'm going to square it to make it positive. And then once I sum up all of these values, all of these differences, then I'm going to divide it by n. So compute the population variance for the San Francisco temperatures. Here were the temperatures. I need to first calculate the mean. So if I sum up all the data points divided by the 12, we've got 12 values, we get a mean annual temperature of 57.5 degrees. Move back up. And then step 2, for each one of these population values, I'm going to subtract there. I'm going to get the different distance from x sub I from that mean. Okay, so these values are shown in the second row. So here's the x sub I for January, February, March, April, and then I'm going to take that 51 minus, here's the 51 minus the 57.5. I get negative 6.5. Now notice these are some of these are positive, some of these are negative. If I just added these distances up, they're going to be pretty close to 0. They're going to average out to be 0. So that by itself is not going to give us a good, useful number if I just added those up. So what I need to do is square them, turn everything into positive. And what's going to happen is the larger numbers, when I square them, that's going to contribute more to this variance number that I'm going to work with. So square the deviations to obtain the quantity x sub I minus mu square. These values are shown in the third row. So these are just square this value, each one of those, and notice that the bigger the distance is for that data point from the mean, the bigger the square value is. These things that are pretty close, they contribute very little. Okay, so this is a measure of kind of a weighted measure. The more farther you are from that data point, it makes it bigger. And if you're very tightly centered around that, then it's going to be a very small number. So then I'm going to go through and add these up. Here's my step 4, sum the squared deviations. These are called the squared deviations. Squared deviations to obtain that quantity. That's the sum of the x sub I minus mu squared. And then if we do that, that's 169. And then I'm going to divide it by the number of data points, which are 12. And this is the population variance sigma squared. And we're going to use something totally different for sample, and we're going to tweak this calculation a little bit, so we have to be very conscious and then report it exactly what this thing is, the sigma squared population variance. So now we're going to move on to the sample variance. Move this down here. When the data values come from a sample rather than a population, I call this, the variance is called the sample variance. Okay. The procedure for computing the sample variance is a bit different. It's basically the same, but in the formula, the mean is replaced by the sample mean. So now this is sample data, so it's sample mean. And instead of that sigma, that Greek little sigma, we're going to talk about S. And this S squared is the sample variance. Okay. And here, when we were dividing by n before, if it's sample data, I'm going to subtract it n minus 1. And the reason we do this is that we don't have all of the data, and this tends to be a better estimate of what the population variance would be. So why divide by n minus 1? When computing the sample variance, we use the sample mean to compute the deviations. For the population variance, we use the population mean. It turns out that the deviations using the sample mean tend to be a bit smaller than the deviations using the population mean. If we were to divide by n when computing a sample variance, the value would tend to be a bit smaller than the population variance. So it can be shown mathematically that the appropriate correction is divided the sum of the squared deviations by n minus 1 rather than n. That would give us a better estimate of what the population data would be. A company that manufactures batteries is testing a new type of battery designed for laptop computers. They measure the lifetimes and hours of 6 batteries, and the results are 3, 4, 6, 5, 4, and 2. Find the sample variance of the lifetimes. So how are we going to start out? We're going to find the mean of these data points. Then we're going to go through and do the deviations, subtract each one of these from that mean. Now we're going to use mu or x bar, sigma, s. Since they measure the lifetimes and hours of 6 batteries, these are only 6 batteries. I don't think that's all the batteries they do. So we can pretty much sure that they're talking about the sample. And it says find the sample variance. Okay, so we're going to use x bar, and then we're going to do s squared, and we're going to divide by n minus 1 when we do those deviations squared. So here's the sample mean, x bar. I divide up all the data, add up all the data points up top, divided by the number. There's 6 of them. That's equal to 4 if we did that on a calculator. And then we go to the sample variance. We have to get this first to use in this formula. So from each one of these data points, I'm going to subtract that off. 3 minus the 4, 4 minus the 4, 6 minus 4. Square these out, and here's these things written out. Each one of these numbers, that gives us 10. And since I'm talking about sample variance, I've got to subtract 1 from the 6. 6 data points, I'm only going to divide by 5. So the sample variance is 2. So compute the standard deviation of a population in a sample. Once we do the variance, the standard deviation is given. It's just basically going to be the square root of those numbers. Remember, they were either sigma squared or s squared. We're going to take the square root to get rid of the variance part of it, and that'll be the standard deviation. And we'll just use the correct symbol for the population or the sample. So because the variance is computed using squared deviations, the units of the variance are the squared units of the data. For example, in the battery lifetime example, the units of the data are hours, and the units of variance are squared hours. So those were the differences, but when I square them, I get squared hours. And I really can't compare that to the mean, squared hours and squared hours. So I would like for those units to be the same, and I accomplish that by just taking the square root. Okay, we do this simply by taking the square root of the variance. This quantity is called the standard deviation. The standard deviation of a sample is denoted by S. I drop the squared, and the standard deviation of a population is denoted by sigma. So if I'm given the variance, the population variance, I can find the population standard deviation by taking the square root. And if I'm given the standard deviation, if I need the variance, I just square it, multiply it times itself. That's what that means, just multiply it by itself. And we'll work on this, on how to do this with a calculator in class, lab. So the sample standard deviation, S, take the square root of the S squared, the sample standard sample variance. And if I'm given the sample standard deviation and I need to know the variance, I just square that number and that would give me the variance. So the population variance of temperatures in San Francisco is sigma squared. That variance is equal to 14.083. Find the population standard deviation. I'm just going to go to my calculator, enter 14.083, and do the square root operation on it. The square root says what number squared, it gives me that. So if I do this, square root of 14.083, that's 3.753. So if I had the standard deviation, I would do the squared operation, enter 3.753, do the squared operation, it would give me 14.083. So the variance of the life science for a sample of 6 varieties, that was 2. Find the sample standard deviation. I would take the square root of that 2 to give me the S. Here I'm using the sigma for population standard deviation. The S would be the square root of 2, looking at about 1.414 is that value. We can do this on the TI-84 as well. Again, we will enter the data in the L1. That's just this little table here. And then when we go through, we'll calculate the one variable statistics command, and it will come up with these data. And here, this is where I need to point out, these are the 2 values that it'll give us for this thing. Sample standard deviation, the S of the X's, or the population standard deviation, the sigma of the X's. S sub X, sigma sub X. They're 2 different values, and remember, we have to determine which one it is. If we were talking about population data, we would use this value. If we're talking about this sample, this is the sample value, because this one's going to be divided by n-1, that's n. And you have to be aware of what data you've entered. Was it population? Was it sample? And that will determine which one of these symbols and values you will use. Notice it doesn't matter for the mean. You're going to mu and x bar is the very same value, but you still need to use the correct symbol. Recall that a statistic is resistance of its value is not affected much by an extreme value, the large or smalls in the data set. The standard deviation is not resistant. That's like the mean. If I had some big outliers, that deviation from the mean is going to be squared. That's going to weigh much heavier into the calculation. So that is, the standard deviation is affected by extreme values, or is it not resistant to those? So here's back to our tables. Go back up here so you keep up with it. We did group data when we approximated the mean using group data. Those were data that had been listed the frequency within a class. We're going to do the very same thing, and in fact, we're going to have to do that mean to start with. So sometimes we don't have access to the raw data in a data set, but we are given a frequency distribution. That's that table. In these cases, we can approximate the standard deviation using the following steps. Now we're given the table, but if this was given to us in here's the histogram, the bar chart, if you will, that contains all the data, we can go backwards and do the frequency distribution from that. So it's very much the same process. I compute the midpoint of each class. How did I do that? I took between the 2 lower limits of 2 consecutive classes, added them, divide by 2, that's the midpoint for each one of those, and then I'm going to multiply times the frequency, sum those up, divide by the number of the sum of the frequencies, and that's going to give it to me. So here, for each class, subtract the mean from the class midpoint to the midpoint minus the mean. That's the deviations once I've got the mean from before. Midpoint minus the mean. I'm going to square it. That's the deviation squared. And then multiply by the frequency. I'm going to add up these for each class. And then I'm going to divide it by n minus 1 if it's sample data, n if it is which is the sum of the frequencies if it's population. So to compute the population variance, divide the sum obtained in step 4 by n, which is the sum of the frequencies, or compute the sample variance, divide this for the sample, divide the sum obtained in step 4 by n minus 1. Since this was the variance, right, this is either population or sample variance, we're going to get the standard deviations by taking the square root in each case. So here was the following table presents the number of text messages sent via cell phone by a sample of 50 high school students. Approximate the standard deviation of the number of messages sent. So we're going to calculate the midpoint of each class. Here's the midpoints. 50 plus 0 divided by 2, 150 divided by 2, 250 divided by 2. Then I'm going to do the deviations, the midpoint minus the mean, midpoint minus the mean that we had calculated before, times the frequency. We're going to add these up all the way down. And since we're talking about the sample, we divide by n minus 1, which was the 50 minus the 1. And then finally, this was the variance, the sample variance. We want the sample standard deviation. This is what we want to work with. This is our ultimate goal. These are the same units as the mean, so we can kind of determine things, as we'll find out in a little while. Okay, so if we put this, we can do group data as well in the TI-84 Plus. We can do the L1. If we put the midpoints into our L1s, the frequencies in our L2, that's that second table or list 1, list 2, and then we do the 1-bar stats, and we just have to tell it that we're going to do L1, L2, which is those that lets it know that we're talking about basically a histogram type situation that we'll run through. And then we'll be able to get whether it's the sample standard deviation or the population standard deviation. And here's the midpoints that they're using in the L1 list, the L2 list is the frequencies from our data. Okay, so I'm going to continue this on in just a short. We'll finish this up as a separate little section. See you back in a little while. Take a break. Hope you have a good day.